All right, so get ready, because with this deep dive, we're going to try and wrap our heads around something pretty wild. Quantum physics at absolute zero.
Definitely fascinating stuff. And the paper you sent over is, let's just say it's a doozy, a deep, deep dive into the Bethe equation, specifically at absolute zero.
I got to be honest, even hearing Bethe equation makes me wish I had paid a little more attention in physics.
You and me both.
So for those of us who didn't spend our free time with quantum mechanics, can you give us a quick rundown of what it is? What makes it so important?
Yeah, so the Bethe equation, it's pretty intense math, no way around it. But think of it like this. It's a tool that helps us understand how particles in a system, like atoms in, say, a metal, how they interact with each other at different energy levels.
So kind of like a map of the energy levels inside this quantum system.
Exactly, a map, a blueprint, yeah. And the really cool thing is that this paper, it looks at how this map, this blueprint, it totally changes when you hit that extreme temperature. Absolute zero.
See, now that's what throws me. I always pictured absolute zero as this chaotic, unpredictable state. Like everything goes completely nuts at that temperature, right? But this paper is saying it's the opposite.
It's a really common misunderstanding. You'd think absolute zero would make things crazier, but actually in a lot of ways, it simplifies things.
Really?
Yeah, it's like, okay, imagine a room full of people all moving around, bumping into each other, total chaos, right? But as it gets colder and colder, things slow down. People start pairing up for a dance. And eventually, at absolute zero, everyone's paired up, moving together in this really organized way. That's kind of what happens at the quantum level.
So instead of a wild party, it's like everyone suddenly decides to waltz.
Exactly. And those dance partners, those are what we call string solutions in the Bethe equation. They're these specific solutions that become super important at absolute zero.
Okay, so we've got our dancing particles all paired up. But how do we actually figure out what's going on at the mathematical level? I'm guessing there's some pretty intense equations involved.
You guessed right. And this is where things get even cooler. The researchers, they found a way to count these string solutions, these dance partners, at absolute zero. And they did it using this really neat mathematical tool called the Möbius Inversion formula.
Möbius? Wait, doesn't that have something to do with those crazy twisted loops? The ones that are like one-sided?
You've got a good memory. It's amazing how these abstract mathematical ideas pop up in places like quantum physics. It's like the universe has a weird sense of humor, you know?
That's wild. Okay, so we've got these string solutions, the paired up particles, and we can count them using a formula based on a twisted loop. I'm with you so far. But what does this tell us about the system itself? Why does counting these pairs matter so much?
This is where we get to the real meat of the paper. The number of these string solutions at absolute zero, it directly connects to something called weight multiplicities in the quantum system.
Weight multiplicities. Okay, you've officially lost me. I need a translator. What in the world does that even mean?
All right, so picture those dance partners again. Each pair has a certain amount of energy, right? The weight multiplicity basically tells us how many different ways those dance partners can arrange themselves on the dance floor while still keeping that same total energy.
Okay, so if I'm understanding this right, we're counting these string solutions, these dance partners, at absolute zero, and that tells us how many different ways they can be arranged on the dance floor, still with the same total energy. And that's what those weight multiplicities are all about.
Exactly. You got it. And this is a big deal because it reveals something really fundamental about the quantum system, something about how many different states it can actually have at a specific energy level.
So it's like we're finding the quantum fingerprint of the system at its most basic level.
That's a great way to put it. And you know, it's really cool. Remember we were talking about that Möbius inversion formula earlier?
Yeah, that thing. Can't forget about a mathematical formula inspired by a twisted loop. That's not something you come across every day.
Well, get this. It turns out that formula, the one that helps us count those string solutions, it's also a key part of this whole other branch of math called combinatorics.
Combinatorics, now that does ring a bell. Isn't that basically the study of counting and arranging stuff? Like, how many ways can you arrange a set of objects? I don't see how that connects to quantum physics at absolute zero.
It does seem like a weird jump, right? Quantum physics, it's all about the tiniest particles, and then you have combinatorics, which seems so, I don't know, it's like comparing apples and oranges. But that's what's so awesome about this paper. It found this hidden bridge between these two things.
So we're talking about a secret passageway between what seemed like totally separate things.
Exactly. And just like when you discover a new wing in a library, you never know what you're going to find. This connection between quantum physics and combinatorics, it could unlock some really cool insights.
Okay, now you've got to give me at least a sneak peek. What kind of insights are we talking about here? What makes this connection so important?
Well, for one thing, it makes you wonder if the language of quantum physics, which can seem super abstract and complicated, if it's actually rooted in something much more fundamental, something, dare I say, elegant.
You're saying under the hood of all these complex quantum equations, there might be a simpler, more intuitive explanation, something based on the principles of just counting and arranging things.
That's the idea. And if we can crack that code, figure out how that connection works, it could totally change how we understand and work with the quantum world. Imagine, instead of grappling with these crazy hard equations, we could use elegant combinatorial principles to understand and predict how these systems behave.
That would be incredible. Like finding a universal translator for the entire universe.
Precisely. And the implications are huge. Think about how this could impact material science, computer science, cryptography, even...
Okay, slow down, slow down.
Yeah.
I'm still trying to wrap my head around that. How would this new way of understanding quantum physics actually translate to these real-world things? Give me an example, something concrete.
Sure, let's take quantum computing. One of the biggest hurdles right now is understanding and controlling how qubits interact. You know, those quantum bits that make up a quantum computer.
Right, and those interactions can get incredibly messy.
Exactly. But imagine if we could analyze and predict those interactions using these simpler, more elegant combinatorial principles. We could potentially create much more stable and efficient quantum computers.
Okay, that would be huge for sure.
Yeah?
What about material science? What kind of impact would this have there?
Oh man, the possibilities are endless. Imagine designing materials with properties we've never seen before. Superconductors that work at room temperature, ultra-efficient solar panels, you name it.
This is blowing my mind. We started with a paper about the big equation, and now we're talking about revolutionizing entire fields, like quantum computing and material science. But it sounds like this research isn't just about the practical stuff, right? It's about changing how we understand the universe at a fundamental level.
Exactly. That's what makes this paper so exciting. It shows just how interconnected different branches of science and math really are. There's still so much we don't know, and it's at these intersections where seemingly unrelated fields collide that the most groundbreaking discoveries happen.
It's like they say, you know, knowledge is knowing that a tomato is a fruit, but wisdom is knowing not to put it in a fruit salad. Sometimes the coolest stuff comes from connecting things that seem totally separate. Except in this case, we're not ruining any fruit salads. We might actually be on the verge of revolutionizing our entire understanding of the universe. I gotta say, my brain's doing backflips right now. We went from diving deep into this Bethe equation to talking about rewriting the rules of quantum mechanics, all because of this link to combinatorics. Who knew, right?
And the craziest part is, it all started with this idea of absolute zero. Really shows you what happens when you push the limits of science, go to those extremes, even if they're theoretical.
It really does. Though speaking of theoretical, getting to absolute zero in a lab, that's impossible, right? So how do we actually use this knowledge? Is it all just a thought experiment?
That's the million-dollar question. And you're right, absolute zero, it's more of a concept. We can get super close, but actually reaching it, that's a no-go.
So where does that leave us? If we can't actually recreate these conditions, does that mean all this research is just, interesting but ultimately useless?
Not at all. Even though we can't hit absolute zero perfectly, every step we take towards it, it reveals more and more about how these quantum systems work. It's like, imagine you're walking towards the horizon. You might never actually reach it, but every step you take, you see more of the world around you.
Ah, I get it. So it's a benchmark then, a way to understand these quantum systems in a way that we just couldn't before.
Exactly. And this research, with this whole combinatorics thing, it gives us a whole new set of tools to tackle those challenges.
Well, this deep dive has been honestly mind-blowing. We started with one research paper, and now we're talking about quantum physics, absolute zero, even a bit of math thrown in there for good measure.
Hey, the pleasure was all mine. It's not every day you find someone so eager to explore these topics, so thanks for that.
I bet our listeners are feeling pretty fired up about it too. So as we wrap things up here, what's the one big takeaway you hope they walk away with from today?
Just this. The universe is full of surprises. And sometimes, the most groundbreaking discoveries come from the most unexpected places. I mean, who would have thought that the math of just counting and arranging stuff could hold the key to understanding the quantum world, right?
I love that. What a great reminder that there's always more to learn, more connections to find, and honestly, even the most complex ideas, they can be broken down and understood if you know where to look. Huge thanks to our expert for joining us on this incredible deep dive. You've given us a lot to think about, And I don't think I'll ever look at a twisted loop the same way again.
Right back at you.
And to all of you listening, thank you for joining us on this journey into the quantum realm. We'll be back next time with another deep dive into the world of cutting-edge research and mind-blowing discoveries. Until then, keep exploring, keep asking questions, and most importantly, never stop learning.